Hello, welcome to the next lecture on analytic function. This is our fifth lecture on this topic. Let us start. First, we have Cauchy's integral theorem. So, what is this statement or what is an proof? If fz is analytic throughout a simply connected bounded domain D, then for every closed contour C in domain D, we will have integral of C fz dz equals to 0. Now, we will have the proof of this statement. The Cauchy's proof of Cauchy's integral theorem is elementary. It depends on the two-dimensional form of Stokes' theorem and requires the additional assumption that f dash z, first derivative of z fz, is continuous. So, for the theorem, we have Stokes' theorem statement. If A is a vector field whose components possess the continuous partial derivative in the calculation of del cross A in domain D, then we have Stokes' theorem. Integral of C A dot dr equals to integral of overall the surface del cross A dot ds, where the surface integration extend over the surface bounded by closed contour C. If A is two-dimensional vector field having the components Ax and Ay, then equation 2 reduces to the form. So what we have the form? We have in LHS A dot dr is Ax dx plus Ay dy, and in RHS del Ay upon del x minus del Ax upon del y equals to dx bracket dx dy, where C is closed contour lying in the xy plane and S is the surface bounded by this contour. Decomposing fz and z into real and imaginary parts means fz equals to u plus iota v, where z equals to x plus iota y. Now we get integral of integration over all the C contour fz dz equals to function fz is u plus iota v and dz is dx plus iota dy. So we can write this in the simplest form, u dx minus v dy plus iota v dx plus u dy over all the contour C. Transforming both the integrals on RHS side of 4 into surface integrals by the use of 3. What we get? Fz dz over all the contour C integration as minus del v upon del x minus del u upon del y dx dy plus iota del u upon del x minus del v upon del y dx dy equals to 0. By virtue of Cauchy-Riemann equations, we have del u upon del x equals to del v upon del y and del v upon del x equals to del u upon del y. Okay, so now next topic is Cauchy's integral formula. First we will have the statement, after we will prove. The most important consequence of Cauchy's integral theorem is the Cauchy's integral formula. This formula and its condition of validity may be stated as follows. What is the statement? If fz is analytic and single valued within and on a closed contour C, and if fz0 is any point within C, then we have fz0 equals to 1 upon 2 pi iota integration on contour C fz upon z minus z0 dz. This is Cauchy's integral formula, where the integral is taken in the counterclockwise sense. Okay, now we will have the proof. Although fz is assumed analytic, the function phi z equals to fz upon z minus z0 is not analytic at the point z equals to z0. Hence, Cauchy's integral theorem is not applicable on the contour C for the function phi z. Okay. Let us describe a small circle C0. Here is the small circle C0 of radius r about z0, which lies entirely within C. Okay. Now, the function phi z is analytic in the region between C and C0. Okay. By making a cross cut joining any point of C0 to any point of C. We form a closed contour C dash within which phi z is analytic. So that Cauchy's integral theorem applies. So we can write integral C dash on the contour C dash. We have phi z dz equals to 0. Means integral over C dash fz dz upon z minus z0 equals to 0. In transversing the contour C dash in the counterclockwise sense, the cross cut is traversed twice, once in each sense. Hence, it follows integration over C dash fz dz upon z minus z0 equals to integration over C fz dz upon z minus z0 minus integration over C0 fz dz upon z minus z0 equals to 0, where all integrals are taken in counterclockwise sense. Hence, we can write integration over C fz dz upon z minus z0 equals to integration over C0 fz dz upon z minus z0. Writing fz equals to fz0 plus fz minus fz0 on RHS, and remembering that a constant may be taken out from under the integral sign, we get integration over a closed contour C over a contour C fz dz upon z minus z0 equals to, by putting the value of fz in RHS which we have written in above sentence, fz0 integration over contour C0 dz upon z minus z0 plus integration over C0 fz minus fz0 upon z minus z0 dz. Now on C0 we have z minus z0 equals to r e to the power iota theta. So dz equals to iota r e to the power iota theta d theta. So that on closed contour C0 we have dz upon z minus z0 equals to integration over a closed path C0, we can write the value of dz and also z minus z0. So we get the value iota integration over a closed path C0 d theta equals to 2 pi iota for every positive r. So we have fz is analytic and therefore continuous at z equals to z0. Hence, for every positive real number epsilon, however small, there exists a positive number delta such that fz minus fz0 in the mod is less than epsilon. So that we can write in the mod integration over C0 fz minus fz0 upon z minus z0 dz is less than or equal to fz minus fz0 in above and in below z minus z0 dz. So by putting the value of the function we get epsilon, and our integration overall closed path d theta, integration on the closed path d theta equals to 2 pi epsilon. Okay, but in the limit r equals to z minus z0 tends to 0, epsilon tends to 0, and since the other two integrals in equation 3 are independent of epsilon and in the view of equation 4, hence the value of the integral in equation 5 must be equal to 0. Then equation 3 we can write integration over a path C fz dz upon z minus z0 equals to fz0 dot 2 pi iota plus 0. Hence we can write the value of fz0 equals to 1 upon 2 pi iota integration over the path C fz dz upon z minus z0. This is the Cauchy's integral theorem. Okay. Now